Human brains have highly complex patterns of connectivity. One way this connectivity can be represented is as a network of nodes and edges. Complex topological features, such as highly connected hubs, can be found in these networks. Recently, generative network models have been used to investigate how brain networks and their topology form. These models grow networks according to a wiring rule. Commonly, this rule emulates the notion of a cost-efficiency trade-off, where connections are formed based on interplay between their wiring costs, as approximated by a penalty on internodal distance, and potential functional efficiency, approximated by some measure of topology, like for instance the matching index, which forms connections between nodes based on the overlap of their neighbourhoods. Varying the importance of each of these terms produces networks with different properties. Model fitness is calculated by assessing how well the empirical statistical distributions of topological features are replicated by the model. Previous work finds the best performing model is one which includes the matching index. However, topology is somewhat abstract and its links to biology are unclear. To address this, we aim to create a more biologically informed model, which may offer a more plausible mechanism of connectome formation. As multiple papers have indicated that connectivity can be predicted by gene expression and cytoarchitecture, both of which are linked to biological and developmental mechanisms that drive connectivity, we devised new generative models that included these measures. First, we measured the correlation between gene expression for each brain region. As correlated gene expression shows a spatial order correlation, we corrected for this trend to remove the slower order effect. Yet this spatial relationship may reflect meaningful physiology rather than just being a confound, so we also use the uncorrected form. We also use measures of microstructural profile covariance by computing the pairwise similarity between each nodal region's intensity profiles for both histology and T1-T2 ratio data, which are considered measures of cytoarchitecture and myelination respectively. Each physiologically constrained measure indexes the similarity between nodal regions for that respective property. These measures are included into the wiring rule by replacing topology or simply used by themselves alone. We found corrected correlated gene expression needed to be combined with a distance penalty to achieve good fits, as both alone poorly replicated brain networks. Most microstructural profile covariance-based measures perform slightly worse than the best topological model, with the exception of the T1-T2 ratio combined with a distance penalty, which did better. The best performing models were those which used uncorrected correlated gene expression, either with or without a distance penalty. However, model fitness is evaluated only based on the statistical distributions of topological features, and does not account for these features' spatial embedding, a key aspect of brain networks. When we examine the spatial embedding of topological features, like for instance degree, we found that the best topological models did not replicate this property. The best physiologically constrained models did show an improvement relative to the topological models, but this replication was still poor. Overall, our results suggest physiological constraints, most notably correlated gene expression, can improve generative model performance. Yet all generative models struggle to accurately capture the spatial embedding of topology.